Okay, welcome everyone. How are you doing? Pretty well? Okay, what's going pretty well? The post lab was not fun. Okay. I don't want to take it show of hands. I would actually kind of disagree on that. Okay. And fun may be a relative term because it's going to get heavy. All right. So it will get heavy in a different way though when we move to ANSYS. Right. And the post lab, which I was supposed to release for what we're going to do today, I was trying to release it so that people would have a little more time on it, but because of the way we're changing things up, I'm a little behind on that. That post lab will be less fun by your definition than what you just submitted. Okay? But we are available and happy to chat during office hours. Okay? So please come by if you're having questions, or send us a message if those times don't work. We're trying to, someone did send me a message saying that I said please come to office hours. So if it doesn't work for your schedule, I'll be a little bit more accommodating over email. Okay. And the TAs are there as well. Just a couple of kind of administrative things to keep in mind. One, please make sure you're here when you take your photo and attendance. Okay, we have some things coming up, and there will be some things happening. Okay, potentially. So we had to look. If you've got an excused absence, okay, please let us. Please communicate with me in advance for hopefully, and we're very accommodating in that. But also let's make sure that we're here when we take the attendance. Okay. And then also with the shared folders, okay, and your assignments, please copy it to your folder as soon as you start the assignment. Work on it in Word Online, okay, and edit it in real time with the real-time sync. Okay, the assignments, the first couple assignments, right, we're getting aligned and everything, right. At this point, though, we want to see the version history looking like someone was actually editing things. Okay, so those are just kind of the couple of things, right. And yes, you might be able to get past us. Okay, I understand, right? It's not worth it though. Okay, it's just not worth it. Every one of these assignments is like not worth that much. Okay, so just do it a day later. Do something else, right? It's just because there's not much value to a lot of things. Just please do it like it's supposed to be done. Any questions on that? Yes.
Especially regarding what you said earlier, will this week be the first week that you're starting with the ANSYS?
No, we're not there yet. We still got, this is another MATLAB day, all right? And then we're going to do finite difference, which will be another MATLAB day, okay? And then we're going to do the same problem we did with finite difference in ANSYS. Okay, so we're going to, and so you'll get to see how they're approached. But we're doing finite difference methods next week in MATLAB. So Professor Singer has it set up so you actually get to code the finite difference method. And then we're going to do ANSYS. So we've got a couple more weeks. So yeah, any questions? Thank you, Jonathan. All right, let's have some fun. So today we're going to be talking about molecular dynamics. And we're going to be extending our treatment of particles to the very, very, very small level, right? So when we were doing the orbital mechanics examples, right, we're at kind of this large scale, Earth and satellite. we then move down to kind of the millimeter meter scale, okay, with a pickleball and with a bouncing ball. And now we're going to the nanometer and smaller scales, okay? And much smaller time steps as well. Okay, so and then we're going to be looking at the physics that are involved with atoms and electrons and charges and things at these smaller scales. So the overarching questions that we're going to be trying to answer through our time together today will add to our experience or our capabilities of modeling interactions between particles. And again, we'll be looking at these interactions at a much smaller scale. So the first kind of question that we can think about is the mechanics of what we're trying to do. Okay? What type of mechanics might we employ to model interactions and collisions between particles? So maybe switch the word mechanics with physics, and let's think a little bit about what we've done with a ball, one satellite, right? So a satellite with no boundary conditions, a ball with a wall, right? But just keeping track of one ball and one wall. Now what happens when you have two balls interacting with each other, or two atoms interacting? What are ways that you can think about them interacting with each other, affecting each other, when they're far from each other, when they're close to each other, when they hit each other? What do you all think? So what kind of physics is going to be involved with modeling collisions and their interactions? Yes. Okay, so yes, we can say, okay, these particles are going to have some momentum, right? So that doesn't go away. So particles have momentum. So we'll break that down into saying they have mass and velocities, right? So if you have, a particle here and a particle here, we could say, maybe this one has some velocity 1, this one has some velocity 2, okay? So that's one way we're going to keep track of things with the physics of these particles. Okay, what else? Yes? Okay, so they could have some charge, most definitely. Okay, would be one, be another feature of their interactions. Okay, and so what are some of the laws that we know about charged particles? Yes, Parker?
Like Coulomb's law?
Yeah, so you have Coulomb's law, right? Right? So positive and negative charges attract like charges, positive, negative charges, they repel each other. Okay? Those are some good laws, or that's a good law. Okay? And so that's an electrostatic interaction. Right? You also could have a charged particle moving in a magnetic field, right? And that would be Lorenz's law, okay? And that would cause it to then curve potentially, because you have the cross product there. We're not going to do that today, but you could have magnetic interactions. Okay, and that would be, for example, Lorenz's law. Okay, and then what else? How else could they interact with each other? First session that we had? Yeah, someone said it, right? Gravity, right? That's the other way they can interact with each other. Okay, now at these small scales, we'll show you that there's something that's kind of a hybrid between gravity and this molecular interaction that can cause a lot of repelling. So what we're going to do today when we talk about molecular interactions is kind of come up with some ways of thinking about relationships where they could both repel each other at some distances, and at some distances they could, in fact, be attracted to each other. Okay. So we mentioned gravity, and if you want the force, you take the negative of the gradient for this, and we've already done this. If you want to think about springs, okay, you have a potential function, right? 1/2 kx squared, 1/2 k delta squared, whatever your variable choice might be, okay? And you have attractive or repulsive forces based on your position from some equilibrium, right? So, you know, you're spreading up the distance between the objects is greater than that equilibrium position, all right? The way I'm defining it, right? They're going to be attracted. The spring's going to pull them back to each other. If you're closer than that, whatever that equilibrium position is, right? It's going to push them apart. And so you can kind of think that networks of springs might be useful when, whoops, that's nice. You like to measure or model a solid. Okay, now, right, we have all this continuum mechanics, well, not a whole lot of continuum mechanics up to this point, but we did a lot in mechanics and materials where we came up with stress and strain relationships to characterize the deformation of a solid object or solid body. And right, solid body is different than a rigid body. So you could imagine, and we're not going to do this, you could imagine setting up a network of springs with masses to kind of look at this behavior. Okay? Springs, of course, are not going to be super great if you're dealing with celestial mechanics, orbital mechanics, because, you know, as the distances get very large and as you get very far from these equilibrium positions, you're saying we have electrostatic charges, so we can have attractive or repulsive forces, and you have this Coulomb constant. We have Coulomb's law, all right, and there is a potential function that we can often think of that ends up giving us this relationship for force. And as we kind of suggested before, you know, if you have positive and a positive, they're going to repel each other. If you have a positive, oops, and a negative, they're going to be attracted to each other, all right? And if you have negative and a negative, they're going to be repelling each other, okay? Now, with what we're doing today, some cases in the homework and in our simulations, what we want to have happen is essentially billiard ball-like reactions. What do I mean by when I say billiard ball-like reactions, right? talked about elastic collisions between a particle and a wall. We can also think about elastic collisions between a particle and a particle. And so, you know, we got a ball sitting on the billiard table, and you, I'm not very good at pool. All right, but anyway, you take the cue ball, right, and you're successful at actually hitting the other ball. Okay? What do you expect to happen? Well, if it's right on, you expect it to send the other ball in the same direction. If it's a little bit off, left or right, you expect it to go off at an angle. So we'll be able to see that type of behavior using electrostatics. In that case, if you're trying to get your balls to bounce off of each other on a billiards table, right? What would be your assignment of charges to those balls? Yeah. Yeah, they got to be like charges so you have a repulsive effect. So, and once again, foreshadowing, if your time step, right? Remember, we're still using numerical methods to solve these problems. If your time step is too large, you could be on one side of the ball, and then on the next time step, you know, just using that velocity and not having the interaction, you could get on the other side of the ball. So you could end up getting spit out the opposite direction than you want to be spit out. Okay? So what you'll see here is that time step is also extremely important when you're modeling these types of relationships between particles. And then we have what we call molecular parapotentials. Okay, so in this case, or in the cases that we'll be talking about, all right, you can have a more complicated potential function than what you have for gravity, or what you have for springs, or what you have for electrostatics. And based on where you are, okay, still conservative field, if you go small enough time steps, you're going to get to see some interesting emergent behavior that is not just 100% repelling or 100% attractive. I mean, springs are not that, right, depending on where you are relative to equilibrium, so they're kind of a little bit of a hybrid of this, but the spring is going to behave the same way, at least it's going to have the same magnitude of force for the given amount of distance from the equilibrium position. Okay? When we start looking at some of this molecular dynamics, that's not the case. Okay? If you squish things really, really, really close to each other, they really don't like that. We'll talk about that a little bit in a moment. Okay, and then these molecular parapotentials. Okay, what we're referring to here, okay, with a parapotential, is that the dynamics, okay, are going to be determined by distances, okay, and the forces need to be significant with respect to the mass of the interacting particles. So let's just talk a little bit about what we mean when we say a parapotential. So if you have a particle and you have another particle, and let's say they're repelling each other, they're a pair. Okay, you're like, okay, fine. And they interact with each other so nicely, or not nicely. Okay. Now, what happens when I add a third particle? Okay. Well, you already can see here that this is not going to be a love triangle, okay, because the first pair doesn't get along. Okay, they separate from each other, all right? Well, I guess maybe it could. I guess this still could be a okay, never mind. I don't know enough about this stuff. All right, so let's say that this has some prescribed velocity, or that there's some force there. This would be another pair that's interacting, all right? And da-da-da-da, this would be another pair that's interacting, okay? So in this case, maybe they're all of the same. If it's an electrostatic case, maybe they're all the same charge, and they don't want to have anything to do with each other. There are 3 particles, and there are 3 pair potentials, right? So if we were to say, okay, this is particle 1, 2, 3, all right, the interacting forces that we could have would be, okay, how is particle 2 imparting a force on particle 1? How is particle 1 being affected by particle 3? And then how is particle 2 being affected by particle 3? Now, these are going to be equal and opposite. Okay, so you also, if you have an F12, you also have, okay, what is particle 2 experiencing from particle 1? So that would be an F21, right? So you have these kind of corresponding forces acting on each other. And so when we work on the homework, you're going to get to see that you have 3 particles. You know, we'll start with 2 particles, and then we'll go to 3 particles. And it's possible that, you know, if one particle is way out far from the other 2 particles, not much is going to happen, right? Or it's possible that all 3 particles are kind of far from each other. But if one of those particles has some velocity and gets into the other particle's space, okay, then we can begin to see some interactive behavior. Now, if these particles have a lot of mass, like it says here, right, forces need to be significant with respect to the mass of the interaction. If they have a lot of mass, then and relative to the forces that are being generated or involved, then you're not going to see much in the way of motion. Okay? But if the forces are significant relative to their mass, then you're going to see a lot of acceleration. Okay? So ways that pair potentials can collide with each other can once again be through gravity. Okay? And gravity can act over a large distance. Gravity is attractive. You can't necessarily get the repulsive bounce, okay, in the respect of, you know, if I have 2 particles that come closer to it. You can do things where, you know, one planet comes around another larger object, right, and gets slingshot out the other way. That's a possibility. Okay, but you don't. But gravity is kind of just is going to be attractive. And then once again, you can have springs. Okay, and like we said before, you can't necessarily get them to bounce away and still have a ton of momentum. Electrostatic forces. Okay, these can be attractive or repulsive, right, depending on what their charges might be. And then the molecular interactions are going to, we're just going to say they're more complex, and they can have van der Waals interactions. So what happens here with van der Waals interactions is, let's say you have, you know, 2 gas particles. At some distance, they want to actually be together, okay? But once their electron orbits begin to overlap, and this is not a covalent bonding thing, right? That's a different thing, right? So these are like particles, like, for example, argon or xenon gas particles. Then when they get too close to each other and they have a lot of overlap, they get in each other's space, they get very upset with each other, and they cause a very fast. They can create a very large force, causing them to separate. So, up to this point, you could say we've had one particle in our simulations, and we've been keeping track of, well, velocity, position, acceleration, right? We've been keeping track of that object, right? So in orbital mechanics and in the bouncing ball, right, we were keeping track of velocity, position, forces, acceleration of these objects. Okay, and that's what you. It's a fine approach. And if you start dealing with more than one object, you have to start making decisions about how you want to keep your counting. So an object-oriented approach would be, all right, I have, particle 1, and it's got attribute 1, 2, 3, 4, right? And I just do it like this. Particle 2, it has attributes 1, 2, 3. You get the idea. Particle 3. This is one way to keep track of things. It's not how we're going to keep track of things for this lab. Okay. What we're going to do instead is, so you could think of, all right, particle 1 has a column vector. This is what would be an object-oriented approach, which we're not going to do. Would have some type of R1, V1, F1, F2, right? And particle 2 would have some type of R1, V1, F1, well, maybe that'd be like, better would be like F12. Maybe there's another particle, F23, so we've got like an F2, 1 and an F2, 3, or this would be F13, sorry. Okay, so this is how we could keep track of things with an object-oriented approach. We're not going to do this. Instead, what we're going to do is keep track of their attributes in separate arrays. So we kind of did this a little bit. You could argue when the lab, post-lab today says, okay, I want you to plot potential energy, kinetic energy, velocity, all these things versus time. So you kind of have an idea, okay, well, I can come up with velocity vectors or velocity containers or speed containers. I can come up with a potential energy container, right? So you have kind of this idea, right? Because you would, for one particle, all right, one particle, it's kind of like object-oriented or non-object-oriented. It's kind of the same thing. But then what you would probably do is, with a second particle, without us saying anything, well, maybe half of the class would do this and half of the wouldn't. Half of the class would say, okay, I want to do object-oriented approach. So I had one array V1, let's say, for particle 1. And then I have a V2, and I'll keep track of all my particles. All right, like my V2 will be my particle 2, right? In the non-object orientation, all right, what we're going to do is say, here are all the x components of position. Here are all the y components of position. Here are all the z components of position. And then each one of the rows in these column vectors is a different it's not a big deal. And it actually, it's right, it's not really that big a deal, okay? But it's just important to make this distinction. So, you know, just this location is the x position of particle 1, and this is the nth position. Or sorry, see, there you go. It's the x position of particle n, or n in lowercase. Okay? So we're just accounting for things in terms of their attributes, and then having vectors that have the length of the number of particles. The similarly, right, you can do this with the velocities, right? So now u would be the x velocity, v would be y velocity, w would be the z velocity, right? So these are now the x velocities, or x speeds if you want. These are the y speeds, okay, or the y component of velocity, however you want to look at it, z component of velocity. Okay. And we can do the same with forces. Now, this is where things get a little bit more fun, or a little bit trickier. Okay. So we still have a column vector to represent all the x components of force. Okay. But it's actually a summation of multiple column vectors because you have multiple interactions, right? So fx11 would be, how does the first particle contribute to a force in the x direction on itself? And, well, usually for rigid bodies, like we're dealing with, for particles like we're dealing with, it's negligible, all right? It's like hugging itself. It can love itself, but it's not going to be giving it, you know, any applied force and changing its acceleration. But you can begin to think, oh, well, you know, particle 2 can exert a force on particle 1, right? So the way this is defined here, right? So this would be this one right here. This would be force in x direction on particle 1 from particle 2. Okay. And then this one over here is the flip. Right? There's a negative sign, but I could have just written fx21, okay, and it would say, okay, that's equal to negative fx12. So in that case, the second row is thinking about, this is how particle 2 is being affected by particle 1. And they're mutually and opposite. They're mutual and opposite. If I have a third particle in the mix, I have now particle 3 interacting and acting on particle 1, and I also have particle 1 acting on particle 3, okay? And so forth. Particle 2 and 3 are also going to be acting on each other. So then you have to keep these interactions, right? So all these different base pair interactions. So for every base pair interaction, okay, for every unique base pair interaction, okay, you have one sub-column vector with two non-zero components. Okay. So 1, 2, right, and then you have 3, you have 2, 3, we add all these up to each other, with each other. And then we can do the same thing with f sub y and f sub z. Okay. So let's just do kind of a little abstraction here. If I have 3 particles arranged like this, and we'll call this coordinate system in which they're acting x, y, and it's a 2D system. And we have interactions between all these particles. And this is 1, this is 2, and this is 3. This is F12, this is F21, this is particle 3, F31, this is F13, and this is going to be F23, and this is going to be F32. Right? If I'm interested in the X positions and the Y positions, these are pretty straightforward. We have X1, X2, X3. We have Y1, Y2, Y3. Now, what would you put for the Fx column vector? The overall column vector. Yes. Okay. Sure. I'm going to say that's a 0. All right, 0, 0, 0, because 1, 1 is not doing anything to itself, or particle 1 is not doing anything to itself. So Fx11 is 0. Fx22 is 0. Fx330. Okay, now. Yes, go ahead.
Fx will be 1 on 2.
Okay, so let's go slow. All right, so this first component, okay, is you're saying you have an F12. All right, that's good. Sure, so you could have an F21, okay, right? Because that's what's acting on, so you see what's acting on particle 1 in the X direction. Not particle 3, right? Particle 3 is only acting in the Y direction, okay? Particle 2 is the only one that's causing anything to happen to particle 1 in the X direction. Okay, so that first line, we're done. Okay, for the second line, what do you think? So what's acting on particle 2 in the X direction? Yes.
There's also the X component.
Correct, right? So we'll say that we have an F23, and we'll just call it sub X. Okay? Now we see what's happening here, right? And for what's happening on particle 3, sure.
Just the X component of.
Yeah. Like that. Okay? So, yeah, we shortcutted all those sub-unique base pairs, right? And what we've created here is one column vector that has the forces in the X direction. Okay? So now let's do it in the Y direction. What's acting on particle 1? Well, we could say F13. Okay, and all of it, because it seems to be aligned in the negative Y direction. Okay. and so you'd have to get the sign right here, right? It should be negative F13, it should be positive F13. Okay. What else do we have acting in the y direction on particle 1? Nothing, right? Nothing. So then what's happening to particle 2? Well, in the y direction, we can see that we have this F23y. We have F23, and we'll call it in the y direction. Okay, so that's this person right here, or that force. And then for the third particle, we can see that we have an F31, right? And we have an F32 component that's acting in the y direction. So we'll say we have F31 in its entirety, and we have an F32 in the y direction. Just like that. Okay. So this is a 3-particle system, and we've now used our non-object-oriented approach to being able to create these parameters that describe aspects of their interactions. Now, once again, we're going to be using the velocity Verlet integration method. Okay? Yes, you could use modified Euler. Well, we could use Euler too, but we found that, just straight up Euler is not super accurate unless you use many iterations for most cases. So in this case, what we're going to need to do carefully is to update these non-object-oriented parameters, right? So the x component of velocity, the y component of velocity, these different column vectors as we march in time through the problem. And you'll find that this type of loop is helpful in being able to sum up the contributions for the unique base pairs. Now, I'm not sure where, if it was me or something else, but there's actually a redundant line of code here that's not necessary, okay? So let's just talk about what's happening. You have, in this case, x component and y component of forces. And when you use the zeros, so if you do zeros of like 2, zeros of 2 would just give you a 2 by 2 matrix, all with 1s in it. Okay? If you do a all with zeros in it. All with zeros in it. Okay? If I do what's being said here, okay, zeros n 1, this is saying n, and in this case is the number of particles you have in your system that you're keeping track of. Okay? It's going to make a column vector of that height, of that number of rows, based on the number of particles that are interacting. And it's only 1 wide. Okay, so that's the column vector. Now, what's done here, and this is clever, is a nested for loop. Okay, where what you're going to do is say, I need to go through all my parameters, all my particles in I, and you can think, okay, this is kind of like, well, it's not the x, and it's not like x, y, and z, right? I is going through all of the particles. So every particle, like 1, 2, 3, 4, 5, 6, right? I is going to go through all those particles, and then it's going to look at I plus 1 to n. Okay, so this is going to go through all those particles and get to a system where it's looking at every interaction, okay, of the other particles on it. You actually don't need, this is a little bit redundant, okay? You don't actually need this, okay? Because what it's going to do is it's already going to be creating essentially a nested loop where it goes through and it looks at these unique base pairs. And so this is actually a little bit redundant right here. So this to this end is a little bit redundant. You can see if you take it out, it'll work just fine. Okay, and you can, but if you want to think about pairs and using it to obey this condition, what you would see is that this would create a 5 by 1 matrix, and ones means that it has 5 ones in it, and then upper triangular would put them above, it put zeros everywhere, including the main diagonal, and then just put ones in the upper portion of that matrix. And so what it's doing is it's identifying those unique base pairs like we discussed, right? So like 1 and 2, 1 and 3, 1 and 4, 1 and 5, okay? And then it doesn't repeat, so when it gets down to here, it's not going to do 2 and 1 again, because it already did 2 and 1 up here, right? It did 1 and 2, right? And then this would be 2 and 1, and it's not doing anything at 2, 2, right? Not doing it at 3, 3. So by creating this matrix and only operating when you're in the portions above the main diagonal, right? This is a 2, 1 interaction, or this is a 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, and 4 and 5. Those are the interactions. And then the fifth particle, right, it's already been interacted by all the other particles. So this is how you can update the interaction, these non-object-oriented parameters for the forces on the particles. Any questions on this? Okay. So let's see if we can get a demo going here. All right. Ooh, oops. Okay. So in this first demo, what we're going to see is the interaction of 2 electrons with each other. Okay? They both have mass, they both have charge, they're both negatively charged. And one is going to be hanging out at the origin of this, quote, cell, and the other is going to be off a little ways, okay, to the left, 3 millimeters to the left, okay? And so what you see here, okay, is, well, actually, I don't know if you can see that. Okay, all right. So what are the coordinates of particle 1's position? What are the x and y coordinates of particle 1? I kind of said it in the picture, but in this code, how would you read it? Sure.
Particle 1 will be a -3, x, and 0.
Yeah. And was I telling the truth when I said particle 2 was at the origin? Was I wrong? I was wrong, right? Where is particle 2 actually? Yes, Safa. In the y. okay? That's a really small number though, right? Okay, so we're saying that's 10 nanometers below the origin. And this thing's starting off at minus 3 millimeters to the left. All right, well, let's have some fun. Well, okay, maybe not so fun. Bear with me. Let's go ahead and let's put that second particle right in line with it. The second electron right in line. Okay, so I've got, and I should have probably said this before. What's the velocity? What are the initial velocities of these electrons? Yes, Jonathan. Yeah, right, right. So particle 2 is got 0 velocity, so sitting there. And particle 1 has an x velocity of 10 to the 5th meters per second, or as Jonathan said, 100,000 meters per second. Okay, so if I put them in line with each other, and I have really good aim, I mean, there's some issues with getting an electron to hit another electron exactly aligned, right? But let's say I'm that good. What do you expect to have happen? Okay, so that's one option. One option is they come and they both split apart. Okay? And if I were to bring them kind of very slowly to each other, okay, you might be able to get to see some of that. I'm bringing them in. I mean, what is slow and what is fast here? The way we've got this problem set up right now, we're bringing it in at a couple thousand meters per second, okay, which is pretty fast. Okay, and so this is going to behave like the billiard ball problem. Okay, so what we expect is that it hits this ball, hits that electron, and sends off the other one, and it's very close to an elastic collision under these conditions. Okay, so we run it, comes in, and then goes to the right. Okay, and you can set up your code so it's doing that draw now business, and it's holding all those frames. Now, just by bringing the electron down, the second electron down, 10 nanometers, you can't see it with the graph itself, but you can see the result. Okay, that red electron was down just a little bit, and then that caused it to kind of graze. That caused more of a grazing type interaction. That caused it to go off this direction and up this direction. This is on square axes. Okay, so this angle is kind of pretty close to what it actually looks like. And so if you look here, the code can spit out that they're off now. Their trajectories, the vectors for their velocities, better said, are about their angle of their velocities vectors is about 90 degrees. You can also look here in terms of what's being reported. Okay, so in the previous, let me go back to the previous example. That's probably easier. We see that the initial velocity is 100,000, and then after they interact, the second electron has a velocity of about 100,000, where the speed of the electron that was over here, okay, where the interaction happened, its velocity is now close to only a meter per second. Okay, so it's not exactly 100% elastic, but it's pretty close. And then when we had them offset, they shared right? They were in a sharing mode. Okay, so most of the velocity is still going into particle 2, right? And we can see that it travels further in a given same amount of time, okay? But some of it's still going to still remains with the first one. So I haven't really done this before, but I'm not quite sure. I don't know actually at what grazing angle will we get. Okay, so we're getting closer to having similar velocities. Okay, but this is, let's see what we have here. Okay, we're getting closer. Okay, so now their momentums or their speeds are about, they're similar. Okay, and actually I haven't really, let's just see. So initially we had, if we had well, actually, yeah, so we have an idea. If energy is supposed to be conserved here, right, we have twice the mass, okay, and we'd have to do 1/2 m1 v squared plus 1/2 m2 v squared, okay? I'm not quite sure if momentum ends up being conserved completely with this given simulation. Let's see. We can kind of do this quick and dirty. Okay, this is going off script. Hopefully it won't cause too much time loss. All right, so we need to say that we have the 100,000 or 10, so it's going to be 10 to the 10 essentially, right? 1/2 of that, and whatever the mass is, right? So we're saying 1/2 1 and 1, right? Right, is if energy is conserved, right? That's what we would have to have be satisfied. Okay, if it's an elastic collision. I'm not 100% sure if it is there. Okay, the M1 and M2, they all cancel with each other, right? So then what we're left with is essentially is this equation. I don't know, I could just handwrite this faster. Okay, is this being satisfied? So, and then the 1/2s all disappear, right? So what we have is 10 to the 5th or squared. I'm sorry. Initial velocity was 2,000, right? No, initial velocity was 100,000. Okay. So that'd be 10 to the 5th squared. That'd be 10 to the 10th. And now we've got 60. We've got 62071 squared, oops, plus 78404 squared. Okay. Oh, that's pretty stinking close. Do you see that? That's pretty stinking close. So yeah, so our momentum is being conserved. Energy is being conserved. Well, you can have conservation of momentum and not necessarily have your energy equation work out correctly, right? Remember that from like if we have a sticky ball, right? It gets stuck in a sticky ball. But in this case, we have 2 separate balls, and the energy seems to be pretty well conserved. Okay, so good. Now, oh, no. Okay. What happens if we have 3 balls interacting with each other? Okay, well, what we see here is ball 1 and ball 2 are aligned with each other, okay, at least in the code, and then the third ball is offset again. In this case, it's offset 10 nanometers down below it, and then once again we see what the trajectory is. Okay, now something that I should have probably said before is this time step has been adjusted appropriately so that we have convergence. But what happens if I go to a much larger time step? So it was at 0.1 picoseconds. Now we're at, what did I change it to? 10 picoseconds. I changed it from 0.1 picoseconds to 10 picoseconds, right? The behavior that we observe is not correct. This is what's happened is the electron has jumped over to the other side, and then the repulsive force is causing that red electron to go backward. So it's important not to forget about making sure things converge, and I better make sure mine converges still for the next time. All right, we've got about 18 minutes left. Let's talk about intermolecular interactions. So imagine you have 2 particles far apart from each other. And there's some type of gravity-like interaction that causes them to get closer, to each other. So then they get to point 2, where there's some appreciable distance r, okay? And that attraction continues. That attraction continues like gravity, okay? Then they get very, very, very close to each other. And when they get very, very close to each other, you had to keep putting more energy in there, actually, if the opposite actually happens, because they don't want to be that close to each other. They actually want to be some equilibrium distance apart from each other. So this is, you could think of it if you had some type of hill-valley system. The ball on this side, of course, what's not true about this system, okay, is that these particles aren't interacting with each other at all, okay? But there is, with the way the potential field is set up, the hills and the valleys, there is an equilibrium position where these balls want to be relative to each other because of the way the field is set up. Okay? That's not what's happening with molecular dynamics, okay? But this is kind of an analogy. And you can imagine that if you have a lot of velocity coming down, you know, if they start way up high, then they can go over that middle hump and they can hit each other. They could bounce off, and then they could like have some interesting. That would be interactive, right? But ultimately, and assuming there's some loss in the system too, so like you have some type of friction, ultimately they would settle into these 2 locations. And that is kind of what's happening with these intermolecular interactions. If you remember, which I wouldn't necessarily expect you to, the gravity potential as a function of distance. Oh, no, what happened? Okay. So this is distance r, okay, and this is the potential function. It looks something like that, okay? And then if you want to go on the other side, looks like something like that, right? And it's kind of like it's going into a black hole. Okay. So as the objects get closer and closer to each other, that gravity potential gets more negative. And the force of attraction goes up quite a bit. Okay? So what you can kind of see here is when the objects are far apart, the slope here, it's positive, okay, in all cases, at least on the right side in quadrant 4, right? It's positive, that slope is, and it's always attractive. But when it gets very positive, at least, well, it's the slope is, you know, the slope down here is very positive, okay? When it gets down here, then it's extremely attractive, okay? And these things just want to be with each other. And in orbital mechanics, right, we wouldn't really, well, like, what do? Boom, they just, like, you know, they get to occupy the same space. But that's not reality, right? You can't have mass occupying the same space. So what you see here is a potential function, this one, right here, this number 1, okay, described by Lennard-Jones. I thought Lennard and Jones were 2 different people. It's just one person. I think. Okay? This potential, if you see here, this like number 2 line or curve, that curve is very similar to the gravity potential. So when you are some far enough distance apart, you have attraction that is akin to gravity. Right? And if I'm going from left to right, that slope is positive on the potential side. So here, slope positive, 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 less positive, but still positive. And remember that the force of interaction is the negative gradient of the potential function. So that means the negative gradient of this means negative. Okay, so that's a negative value, and that's attractive in this case. When I get over to this region, all right, now this is also part of the Lennard-Jones potential, that is extremely not positive. Okay? At least if I'm going from left to right. That's extremely negative, which means if I take the negative of the gradient of that, I'm going to get an extremely positive number. And that's going to give you the extremely repulsive effect. And so Lennard-Jones came up with this potential function. It turns out that is very nice at describing interactions between atoms. Okay, so it's kind of a little bit of gravity and a little bit of repulsion, kind of like 2 like charges that you would see with electrostatics. So this is one way of mathematically writing out this Lennard-Jones potential. And there's a lot of stuff here, okay? This epsilon parameter is called the well depth. And you can kind of see that if that well is really deep, it's gonna, the two, and again, we're talking about these are base, I should have said this, these are unique base pair interactions. Okay, so this is saying, okay, I've got 2 of these like atoms or molecules that are interacting with each other. Okay, and if that epsilon is really deep, that means that they really want to be separated at that distance. Okay, so now we're thinking this is maybe a little bit more confusing, that this R is not like, okay, how far am I from the Earth? This R is actually describing what is the distance between the particles. Okay, so if the particles are far apart, again, you have a gravity-like attraction, but then as they get closer to each other, they really want to, if that epsilon is really deep, they really want to be in that well, and they really want to be in that equilibrium position. What is that equilibrium position? That equilibrium position is given by this distance. It's often called Rm, okay? And this is a van der Waals radius, okay? And this is half the internuclear distance between non-bonding particles. So if we look over here, okay, this Rm, all right, is given by this 2 to the 1/6 times sigma. Okay, what is sigma? Well, sigma is the zero potential. Sorry, sigma is the zero potential, meaning this is where you have okay. So yeah, there's a little, they're close, but they're not exactly the same. I'm sorry, I messed this up. This is where the potential function is equal to 0, okay, and it has a specific distance, right? And you can think of this as half nuclear distance. And then where the well is, this is Rm, and that is given by 2 to the 1/6, okay, or the 6th root of 2 times sigma. And you're thinking, what in the world is this? Well, here's the potential function, and here is the negative gradient of that potential function, or the negative derivative of it. And Lennard-Jones had this thing to the 12th power and this one to the 6th power. So when the distance between these particles is really, really, really small, which one of these terms, the 12th power one or the 6th power one, which one is going to dominate when r is really small? The 12th. Why is that? Who said that? You said it. Okay.
Because you're basing the number at the
Yeah, if you have like 1 over 100, or 1 over 1 over 100, 1 over 1 over 100, you square them, right? That's a lot bigger than just 1 over 100. Okay? Or, that 1 over 1 over, right? So as this gets small, right, the large power dominates. And then as r gets larger, they kind of are like, okay, big number and another big number, it becomes less of an issue. Okay? And so you approach 0. So, when r is big, right, we are approaching 0. When r is very, very small, we're approaching infinity. Okay? And that's what this function that Lennard-Jones proposed allows us to do. Okay, now, you can plot out, if you like, the force as a function of distance once you know the different parameters. And time steps are extremely important here. Extremely, in fact, it's part of it will be part of your post lab. Okay, so if you have small time steps, you can march and reasonable velocity. You can march into the well, and you can stay oscillating in the well. You can go back and forth. If you have reasonable velocity coming in, and you have a very small time step. But if you have large time steps, you can miss your opportunity to be in that well. And then end up somewhere like, well, as soon as you're out here or here, you get extremely repulsed, and you're going to see the particle take off. Right? The particles are going to just want to get apart from each other. Okay? Because they get into that very, very steep portion of the Lennard-Jones potential, which means you have a very large force, and it only takes one time step with a very large force to blow the thing apart. Okay? So let's just do a couple of examples real quick. And maybe you'll want to kind of remember some of these things when you do the lab or the post lab. Okay? So here we have two particles, and they're xenon atoms, and we have all the appropriate functions in place. They're very close to each other. Now they're minus 10 nanometers apart, and it's coming in at 1,000 meters per second, the one on the left. All right, so let's see what happens. Oops, that's kind of an answer. Well, it's what your answer should look like. Or actually, maybe no, it's not. It has different numbers. Okay, so here's the actual physics. Okay, so one particle comes in, boom, it's billiard ball time. Okay, not super exciting, all right? But this is an example where I came in with enough velocity that, and I had a small enough time step that I could get appropriate billiard ball interactions. Now, what happens here if I go to a large time step? Let's say it's right now it's at 0.01 picoseconds. Let's say we go to 10 picoseconds. Yeah, actually, I don't know if it'll even run. Yeah, that's too big because the simulation is not even really running enough time. So let's go to, right, if also not, okay, so let's, okay. Uh-oh, what did I just do? I just broke something. Oh yeah, my floor reporting is only that. So let's see if this will work. Okay, it comes in. All right, is that the behavior we expect? Well, it could be, right? But remember what we talked about, if the time step is too large, it will get too high up on that potential curve, close to the vertical axis, and it will cause an explosion. Because that one time step with a very large force will just repel them. Okay? So, very important to get the right time step. The last thing that is, I hope, helpful, I'm just going to put this back so that oops, okay. Okay, so these are bouncing atoms, okay? Bouncing is what we mean by bonding, all right? You see, they get kind of close to each other, and they bounce apart. They get kind of close to each other, and they bounce apart. And you see that they're still both going in the same direction that you had with the original velocity that the electron or the atom on the left possessed. Where did it go? I guess I lost it. Anyway, so these particles, these are bonded with each other, and they are nicely interacting with each other. And they are getting close, but then they pull a little bit apart from each other. And they get close, they pull a little bit apart from each other. And that's how they want to bond. Okay? And everyone needs their space sometimes, right? But they're still going in the same direction. They're still in step with each other. Okay, so just keep that in mind as you both play with the velocity, the distance, and the time step to get this bonding behavior. That pretty much concludes what we're covering today. So hopefully you got an idea of how we create a non-object oriented approach to keeping track of the properties of the particles, and then you also have an idea of how we can model complex interactions using potential functions. Okay, let me stop and let's do the attendance.